Okay, good morning everybody. I hope everyone's having a wonderful day. So, today we're going to be talking about a sorting algorithm called merge sort, and then from there we're going to start talking about something called the dictionary, which is going to play a very important role for the remainder of the course following this topic. So, last day I sort of planted a seed of a subproblem that'll be closely related to our next sorting algorithm. So last day I did this example where I gave you two sorted arrays, and the idea is that I would like to merge them into one longer array that is sorted. But here's the thing. It isn't just that these two arrays, keep in mind the idea that we'll have will easily generalize to many arrays if you like, but the idea is that they're already sorted, so we want to use that information to help us design a more efficient algorithm. Because guess what? Well, one very simple way of doing this is by just simply taking the two arrays, copy their contents into a longer array, or if you have them all already in one array, you could just sort that, right? But the thing is, I would like to do this faster. So normally one common thing that you'd like to do when you develop an algorithm is try to exploit the structure of your problem. So in this case, if I know that my two subarrays are already sorted, I want to use that information to come up with a more efficient algorithm. And we're going to see that just like what we talked about partition the other day, that there's this other subproblem that's going to be closely related to merge sort as partition was to quicksort. And this one is called merge. So before I get into merge, I just want to make sure we kind of have a big high-level idea of what we're doing. So remember we've talked up to this point about the idea that, okay, I can look at sorting, not just like this iterative process where I look at two elements and I examine those, right? Instead, I can now look at it as I have a sorting problem instance. I can cleave that into smaller pieces in some way. It's so-called a divide. I want to divide the problem into smaller problems. And I would like to, say, perhaps combine them in some way when I'm done solving these smaller subproblems. This is a so-called divide and conquer algorithm design technique. So in merge sort, we do something just like we did with quicksort, except it's going to feel like we're doing things the other way around, where there's still a divide and conquer phases. But the thing is rather than arranging the array such that I have that L group, the pivot, and the greater group, what I'm going to do instead is I'm going to, because remember last day, we established that the best case, for example, for quicksort is when the pivot is smack dab in the middle position of between the L group and the G group, so they're roughly equal in their size, right? So what if I could just straight up create this kind of setup? So here's the idea. What I'm going to do is because I know how to sort subarrays of size 0 and 1, right? Because they're sorted by definition. So the idea is very simple. I'm going to cleave my array into sizes that are of equally sized halves, just like what we would like to have. And the idea is when I break them down to sizes of 0 or 1, for example, then I know those are sorted. So in the conquer phase, I would like to combine those sorted arrays so I can make bigger or longer sorted arrays. And that brings us to our friend merge. So merge seeks out to solve the following problem. I give you an array where I have some range, where the first position is position P, the last position in this range is R, and I would like to sort this subarray, starting at position P up to and including position R in the array. So the additional assumption we have is that there's actually broken into roughly two equal halves. But keep in mind, in the merge process, it doesn't really make much of a difference. But the point is that there's two subarrays. They're both sorted. That's all we need here to make this work. So I'm going to have n1 many elements in the first chunk and n2 elements in the second chunk. But like I said, although the algorithm is going to cleave them so they're roughly equal in their sizes, it doesn't have to be the case for merge to operate correctly. And here's the idea. If I know that this chunk and that chunk, my n1 elements, my n2 elements, if I have these two, I can imagine them like putting them into two buckets where I always know which one comes first. It's usually the smallest of them, then the next the next largest, then next largest, then next largest, and so on. So here's the idea. I'm going to create two arrays. I'm going to copy those elements in each one of these two groups. You could think of it as just groups, kind of like how I had L and G. So imagine I have these that are sorted already. And I can imagine them as two arrays, I'll call them L and R here because you can think of it as the left and the right. And respectively, I want to play a game. You can imagine like I'm going to play a little tournament. So what I'm going to do is I'm going to keep track of two fingers that are going to be the contenders in our tournament. I'm going to have an I here and a J here. They're both going to start off in the first spots. And now there's something very fascinating about the fact that these two groups L and R are already sorted. Can somebody tell me something that's rather interesting? If I put my fingers on I and J, what can I know about this with respect to all the other elements in L and R respectively? So if I compare this position against that position, what can I say about that? Is there any ideas? Because I want to really get you thinking about like where we can use this information. Well, in our case, we know that yes, 1 will be less than 4, but here's the neat part. If you know, so if I give you, say, 1 versus 4, if I tell you that 1 is less than 4, what else is it less than? If I look at L and R. Everything else, right? It's everything else. So if I compare 1 against 4, it also has to be less than everything else in R, but because I'm currently considering everything in that given position, everything to the right of that is also has to be bigger or equal to than my value, right? So we're going to use this information. So I'm going to have two groups. I'm going to have my team L and my team R, and the idea is I always pick, when I have my contenders in my tournament, I'm always going to pick the smaller of the two. And whichever is the winner of this competition, I copy them into the successive spot for that round. And the idea is I'm going to run around for every single one of these elements until I've determined the smallest to the largest. And I'll be copying them back into this array. And that's actually how merge works. That really is all merge does. So let me recap this and I'll quickly blast through this example because this is the same example from last day. So just to recap, I'm going to create L and R. I copy each half. Now keep in mind, it does not have to be a half to make this algorithm work. It's just that that's the way it's going to play out in merge sort when we get to merge sort. But one thing I'm going to do, as I mentioned last day, is I'm going to introduce another element, a sentinel value. This will ensure that if ever I'm playing this game of a tournament, if one team runs out of players or contenders, that I always have another contender that's way bigger than all the other elements. So that contender is going to be way too big for even other players that are playing in the tournament. This, you might ask, why would we put this in here? Why can't I just put like a little check to say, oh, I'm at the end of the array? You can do that. That's the one thing you can do. But you'll notice that this simplifies the programming of this. Because all now you have to do is just do two comparisons, right? Just in the same principle we had with our fingers, right? Just the difference is when I becomes this position, you know, no matter whatever this is, the other team's going to win, right? So I'm going to keep these two fingers, and I'm going to go starting at position P. I'm going to scan from left to right. For each one of these, you imagine I'm playing a game of which one is the smaller of these two, and I copy whichever is the winner into that position, and then I move its finger over by 1. So the winner's finger gets moved over to the right by 1. And that's really it. That's all merge does. So let me just recap this. So I'm going to quickly kind of run you through this just so you get a flavor for this. I did this last day, but I thought it'd be a good idea I could do it one more time just to stitch it all together. So I will give you the pseudocode. The pseudocode's in the notes. You might ask, Dan, why are you not writing it here? It's because it's a little lengthier than partition is. It's not as long as you understand these three main steps, that's everything there is to merge. It's just that the pseudocode's a little bit more lengthy than for the time that we currently have. So, suppose I gave you this example here. This is the same one from last day. So, in this case, I would want to scan from left to right. So first I would create these two groups. I use these sizes, and you can compute these directly from the indices. If you take a look at the pseudocode, it will actually show you exactly how you can compute them. And once you have that information, you can scan from left to right. So you'd start off at this first position, and it'll start playing the game. So which one wins? In this case, we established that Team L wins in this case. So I'm going to copy 1 into position K, which right now is position P. Notice there's a 1 already there, so I'm just going to rewrite what's in here. So I move over my finger. Now, Team L presents me a 2. Team R presents me a 4. Which one wins, Team L or Team R? Which one wins this time? L, yeah, exactly. Team L wins. So, what means I'm going to copy this 2 into this position. Remember, I would increment K because I'm doing this in a for loop. I would copy over the 2, but notice there's a 2 already here. It doesn't make any difference. I just copy it over. Now, of course, since I've done that, I'm going to increment my finger. I have 3 versus 4. This case, Team L wins again. Now, you'll notice that Team L just seems to be winning. That's just a coincidence here. So, notice I'm just going to copy over the 3, but the 3 is already here, so I'm not going to nudge it with my finger. Next, we increment K. We play the game again. Now, remember, I moved my finger because 3 won. Now, I have Team L presents me a 10. Team R presents me a 4. Which one is the winner? L or R? Yeah, R is the winner this time, so I'm just going to copy over the 4. No, you stay there, Team R. I'm on to you. So I'm going to put copy in 4 right here. We're going to move my finger for Team R, 1 to the right. And now we have 5 versus 10. Team R wins again. So I move my finger to the right by 1. And now I increment for my next round. So the next round, I have 7 versus 10. Which team wins? Because L's got 10, R's got 7. It's going to be R this time, right? So I'm going to copy a 7 in here. I got to move my finger. I'm going to move K up for my next round. No worries, that's okay. So now I have 10 versus 11. Team L or Team R, everybody? Who's winning? Team L or Team R? Yeah, now it's L, right? So I'm just going to copy over. Team R is going to have a nap. So 10 goes into here. I move my finger over here, and I go to my next round. Notice now this is why this is actually handy to put in here. In practice, what this would be is some value that is bigger than all other entries that would be possible in your array. You might use an inbuilt constant, for example. Like if you're working with integers, you might use the integer maximum value, for example. There's inbuilt constants often in some programming languages you can use. Some that function just like this. So I have infinity versus 11. Which team wins? So which one's the smaller one? Yeah, R this time, right? So I just copy over 11. I move my finger, and boom, we're done. But now notice that it's sorted. Now, notice that just like partition, if you walk through the pseudocode, I encourage you to try looking through it. The time complexity of this is going to be n1 plus n2. where n1 and n2 are the sizes of the two groupings that I have here. Which, of course, this is no more than n, right? So it's still going to be linear in the number of elements that I'm trying to merge. So that's how the merge process works. Are there any questions about that? So question, are we creating new arrays or shuffling the original one? So here's the thing. I create these two arrays to play my game of this merge process. This array is the one that comes along with the input. So we're actually modifying these positions in the array A. So this would be something you're directly manipulating. In the algorithm, you actually create these two arrays. So these two arrays right here are brand new. This is the same one that you're sorting. Just like in quicksort, we don't actually build new arrays like this. Instead, we actually just manipulate the array we have initially. That's a good question. Yeah. So you'll notice, so one thing I will point out is that when you do the merge process, you create these two arrays, right, every single time. So technically we're using a bit more space when we do this, right? So this merge process actually uses additional space. In fact, the amount of space is, it's going to end up being that you're going to be using a linear amount of extra space, right? That's a very good observation. I really appreciate somebody bringing that up. But yeah. So this merging process, you can do this. I must stress that there's other ways to represent merge sort. There's an iterative version of it. There's other variants of merge sort. This is the classic. But yeah, no, very good. So now that we have merge, you're going to see that it's going to be very easy for me to now show you merge sort. So let's talk about merge sort. And again, you'll find yourself I'm hoping you'll feel like this thing will look a lot simpler than some of the other sorting algorithms you may have seen before. It's just that, remember, merge does all of the heavy lifting with this algorithm. That's the thing I want you to keep in your mind when you look at this thing. It is very short, just like quicksort is, at least when it comes to the algorithm itself. So here's merge sort. It takes in as input the array A. It has two parameters, start and end, just like we had for the recursive version of quicksort. I didn't write down the driver function. It's the exact same parameters you would have for the driver function for quicksort, where you make that a 0, you make the end n-1. So some of this actually will remind you a little bit of binary search the first time you look at it. And that's not a coincidence, by the way, that it has a very similar structure to it, because we want to cleave, the idea is that we want to cleave our array into two separate chunks, just kind of like binary search does. And just like in our best case for quicksort, we would like to do something like that. So you'll notice I use a very similar setup. So it's going to sort A sub start to A sub end. And it has a similar setup for the recursive case. Remember, when I check if start is less than n, this guarantees that there has to be two elements, right? That means that I've implicitly excluded the base case, because when the base case occurs, you have one element or no elements, right? And by definition, those are sorted. So now what you do is you find a middle position. Note that these are floor signs. When you're actually implementing this in something like C++, you don't actually have to explicitly call a floor function from like a math library. You don't have to do that. It's just integer arithmetic, right? So when you're actually applying with these with using int, for example, you don't have to put the floor in, and it implicitly does this, because if ever you do integer division, it never keeps track of the fractional part, just like I talked about with binary search. So you compute this middle position, and then what you do is you have two recursive calls to merge sort. So you notice that this divide process is going to break this into a whole bunch of smaller subproblems until they're small enough. And then what's going to happen is it's going to apply this merge process. So the one we just talked about over here. Merge takes in 4 parameters. So it has the input array A, has start, mid, and end. So it quite literally is like cleaving it into 2 roughly equal parts. And this merge process combines the two. But remember, what we're actually doing is we're just taking the parts that are in that array and we're just merging them through this merge process. So we're not like, these aren't like literally two different chunks, but here's the neat part about this, is if they were two separate things, like two lists, for example, the same idea applies. So you can actually use this when it's literally like two literal entities that are separate, not in one contiguous thing like an array. So there's a couple other ways you could describe merge sort, for example, using lists, where you're combining a whole bunch of small lists. So you take a bunch of lists, you combine them into larger lists, and you can ever grow them and combine them into one super list. Just as an example. But this should look, I'm hoping that you find this rather interesting, just the way this is set up. One thing I will mention as a historical note, merge sort, so I mentioned about quicksorts, a little bit of the history behind quicksort. Merge sort was developed in the late 40s by the computer science pioneer John von Neumann. If you've ever heard of that name, especially if you're interested in, say, things like architecture, you may have heard of the von Neumann architecture. That's the same computer scientist. He did a lot of different work in many areas of what we would call computer science now. But yeah, just a very interesting historical note. So now, before I'm going to quickly just walk you through just the high-level idea of how you would apply this algorithm, just so you can visualize how this plays out. So, I'm just going to draw a fun picture like I did for quicksort. So first, I'm going to go through the divide phase. That's going to, remember, in this case, we're just going to break it down into tiny, tiny, tiny pieces. And then we're going to rely on merge to combine them. So you're going to see this divide phase, I'm just going to straight up cleave this sucker into a bunch of small pieces. And then the conquer phase is going to do the sorting for me. So imagine I give you this as the array. What I do is I perform two recursive calls, right? I have two recursive calls. So I'm going to have 2, 3, 10, 1. So these start, mid, and end are going to change with each call. So in each one of them, you'll have a mid on its own, but notice it's going to be like in halves, just like you're familiar with some of the algorithms we've seen so far. We have 5, 7, 11, 4. Then, again, cleave it into two roughly equal parts. I have 2, 3, 10, 1. Same thing here. I must stress that technically speaking, when you're actually carrying out this recursion, it would start off probably with the left branch every single way down. I'm just doing it this way to visualize it for you in a way that's a little bit more easy for us to really kind of talk about here in such short, I guess, the amount of time we have. So if you're actually curious about this, if you find yourself curious about implementing merge sort, which I encourage you always to try to do, is if you find yourself implementing it, try printing out what start, mid, and end are, and you can actually find out exactly what I'm talking about, where, for example, you'll see that it actually follows down a specific set of branches downward, then it kind of works its way around to this entire exploration of this call tree, just like in the Fibonacci example, actually. So I have 5, 7, 11, 4, and notice that I have 2 here, so I have 2, 3, so 2 calls will happen because they only have 1 element each. So like I said, if they are not going to cleave perfectly like this, one chunk will have 1 more element than the other chunk will. 11, 4. So this would be what I call the divide phase of this algorithm. So these recursive calls will keep happening until you end up with where you're going to go through each of these one by one, where you're going to have the first call, the second call happen. For example, down here, this would actually be where it probably would happen, where it would have the first recursive call, we'll bring it all the way down here, and then you'll have to solve this one. Since it is a base case, we don't do anything. Then this second call would happen, and then it would call merge on that. So now, notice here that if I apply merge, remember, all I have to do when I'm doing this conquer phase, I'm going to work my way back up to sort the whole thing using the recursion. So watch this. So I would apply merge as I have it over there. So I would just take These are just, you can imagine these as my two chunks. Remember, this will be in the array in a given interval. But the thing is, you'll create two separate arrays for these, then you'd apply merge, and you'd end up with 2, 3. In this case, you'll have 10 and 1. It should become 1, 10. Then now you have two sorted lists of elements, or two subarrays. You apply merge. So you would have 1, 2, 3, 10. Let's do it with the right branch here. 5, 7. Okay, I already wrote it like this. That's technically sorted. I have 11, 4. I'm going to apply merge. So remember, as I'm going back up this call tree, what you want to imagine is I'm applying merge at each one of these steps here. So I'm going merge on every single one of these links that are going down. Each one of them, when I'm coming back up, I'm applying merge. So this is what I mean by the conquer phase is actually kind of like the opposite of quicksort, where quicksort does all the setup to split it into the two pieces. Merge sort, however, hence its name, it uses merge to combine two sorted smaller lists, or arrays, or subarrays. So I have 4, 5, 7, 11. Remember, each one of these is an invocation of merge when this happens. And then, now I have two sorted arrays, akin to something like my example, because they have 4 elements each. And I would just simply apply merge to end up with the final result. So I'd have 1, 2, 3, 4, 5, 7, 10, and 11. So this is the conquer phase of merge sort. So the whole idea here is quite simple. We break it into very, very small pieces. We know how to solve very, very short arrays. To sort those, once we have those, we combine them. And that's what this conquer phase does. So this is all being done by this line in the algorithm. So in each one of the calls, it performs merge after it performs these two recursive calls. And that's what we're actually going through in this process. So are there any questions about this at this point? But yeah, just remember, the recursion is doing a lot of heavy lifting here to break it into smaller pieces. The whole idea here is that when I say break it into smaller pieces, what I'm saying abstractly speaking is I'm giving you subarrays. So I'm trying to make these into smaller subarrays by modifying what start and end are on each one of my calls. And the whole idea is I want to know how many elements do I have left. And whenever that if statement is not it's not satisfied, you have exactly one element or no elements, because the intervals cross over each other. So, are we okay with this so far? Can we show how the sort when you break the whole thing down to single element? So just, can you show how it sorts when you break the whole? So let's see here. So remember, okay, there's two questions here that are really helpful. When we get to merge, what will be mid? It's what's computed right here. Because remember, each call has its own local variables, right? So when I make this call to merge sort here, and this call right here, each will have their own copies of mid when they're computed. So when I use mid right here, this is the same mid I computed on this line. It's not modified at all. So that's the first thing. The other thing is how it's sorted when you break the whole thing down to a single element. So remember, if I have it where I'm doing all these recursive calls, suppose I'm looking, I keep calling recursively merge sort. There will be a point where when I call merge sort, I end up with a single element like this. Remember, this is just a representation of start and end. So since it will not need to do any more of this, it's already sorted, then the second recursive call won't happen. And in that case, it will have one element like this. So if I'm considering the call where start and end are these two elements, now keep in mind I've already sorted it, But what would happen here is this is when you do the merge call. So the whole idea is that you're just applying merge to combine these two smaller parts. But remember, when I actually combine them, I mean I'm going to give you those two. I already have a range of elements, just like in my picture at the beginning of the lecture. Remember, I have N1 elements and N2 elements. This would be the N1 elements. This is my N2 elements. They'll be right beside each other. But yeah, so this is just one step of this process. So remember, the first phase is just breaking this down into smaller problems. The second phase is when you actually attempt to solve it by building up these smaller subarrays into larger subarrays. But just keep in mind that the way recursion operates, it might be doing these calls in a different order than I visualized here. This is what I encourage you to play around a little bit with. Does it actually break down into separate arrays, or does it work on a single? This is all just one array, just to be very clear. But I must stress that you can use merge sort when these are literally different collections of elements. So if you want to have them all as just different lists, you can do that. Merge sort will still work, but in this classic representation of it, I don't change, these are not multiple arrays. These are all the exact same array. I'm just visualizing it for you. Where these parts here, these things in the boxes, those are, for example, this would be start, mid would be right here, then whatever else will be whatever comes after that to the end. But will merge sort also work on an array with an odd number? Yes, of course. Like I said, if they doesn't break into two equally sized amounts, what happens is you just give one element over to the other side. So you know how I talked about the floor and the ceiling, like floor and ceiling functions? What will happen is when you can't cleanly divide, what happens is 1/2 of them goes into n over 2 elements. If I have n elements, say up here, n over 2 would go to one side, and the ceiling of n over 2 would go to the other side. It doesn't matter whichever gets that extra one. Just the point is that you're still making it so they're roughly equal to each other. But that's a good question. So I think technically in this case what will happen is it might be the ceiling first and then it'll be the floor, but you get the idea. The idea is that I'm breaking them into two roughly equal sized chunks. And remember, when I'm saying break, I'm actually talking about the changing of start and end, just like in binary search. I don't actually take the array and cleave it in half. Because remember, if I cleaved it in half, that means I have to make another array, and I would have to copy all those elements over. That's not what we want to do, right? That's expensive. So, anyways, the first thing I want you to do when we look at this picture, this should remind you of something that we did last day, right? Notice how everything's breaking nicely into evenly sized chunks that are roughly like this. For the sake of simplicity, I'm just going to assume, say for example, that say the length of the array is a power of 2, which would always allow it to look something just like this. So, do you remember me drawing you a picture? It's kind of like this. Not necessarily this exact, like this kind of setup as the example, but I drew a whole bunch of recursive calls, but I wrote out how many elements were in them. And I tried counting up the amount of operations that happened. Does anybody remember that? We talked about when we were doing the best case analysis for quicksort, right? So remember here I have n elements. And these two, they're n over 2. And here I have n over 4. And this would be n over 8. And it would keep successfully being broken down until you have either no elements to consider, or there's just one. This should remind you of something we did the other day. It should remind you of the best case analysis for quicksort, right? So if you remember what I said about the time complexity for merge, if you look at our algorithm here, first if you ignore the recursion, notice that the total number of operations is dependent on the number of elements in this range, right? Which, if I'm being very generous, is whatever the number of elements there are in that array, right? So if I were to count these operations, I know merge does all the heavy lifting when it comes to the amount of work that has to happen. for non-recursively. So, for example, at this, if you think of it as levels, like I did last time, the total amount of work that happens here is big O of n, right? And just like we had last day, we have half of them here, half of them there. Well, it's going to be something that's like big O of n over both of these calls. If I add them up, since I have n over 4 of them, there's going to be, again, a linear amount of work that happens over all of these calls. A linear amount of work all the way down. Can somebody tell me how many levels or what's the depth of this recursion? Because what I've visualized for you is actually the depth of the recursion. This is actually how tall the call stack can possibly get. So how tall could that call stack get in terms of big O? We talked about this last day. It's log base 2 of n, right? It's big O of log n, right? If I want to be more precise, it'll be like this. So naturally, if you add up all of the work that happens over all the calls, like we've seen before, and I know how many levels there are to this, the total amount of work, the time complexity, is big O of n log n, right? But remember, that's worst case. So this actually is the first algorithm I've technically presented to you in its entirety that runs in the worst case big O of n log n. And which actually so where does the log, and so remember, like I talked about last class, if you ignore everything on the right branch of the two calls, so if you look at this one, look at the sizes of how many elements are in each one. N over 2, n over 4, n over 8, and it'll go n over 16, n over 32, n over 64, and so on. So if you do this process, you ask, okay, how many times can I cleave this down to the number 1 or 0? And here's the answer. It's actually a logarithmic number of times that this happens. So one simple way I can explain this to you is imagine I give you n. I want to know how many times I can divide by 2 until it's either 1 or 0. And the answer to that question is it'll be something like big O of log n. And if you're not convinced entirely by that, well, think of it. Think of it very much like the analysis we did for binary search. We had something very similar happen there, although we were a bit more precise about it. But we noticed there every time I went down one depth in the recursion, every time the power of 2 ended up in the denominator grew by 1, right? Same idea here. But yeah, if you want the careful details about this, actually I have them in the notes where it actually shows how you can derive this. So I'm going to leave that as a little thing for you to read if you want to take a look at it. So if you're really just not convinced by my explanation, take a look in the notes. I actually walk you through carefully this analysis and where the log 2 of n comes from. So I'll encourage you to take a look at the notes for the details on that. So remember, this is worst case. So keep in mind, that's worst case time complexity big O of n log n. It's not big O of n squared, it's big O of n log n. So that's just better, it's more efficient than quicksort is in the worst case. Unless you use a very specific pivoting strategy for quicksort, like we talked about the other day. But we're talking more in generalities here versus the two. Note that this is also the case in the average case. And for the one I presented you here, it's also in the best case. You'll see very quickly why that has to be the case by the way the algorithm is presented to you. Notice that it still, regardless, cleaves all of these down into small problems. Well, to do this cleaving process, it's going to break them down from n down to sizes of 1 and 0, regardless. It doesn't matter which way you do it. It's still going to be a logarithmic number of times it's going to have to do this, and the merge process is linear time regardless. So notice that this is actually going to be, if you want to think about this carefully from the worst case perspective, and this is something that I actually prove in a class like CS340, is we actually show that this big O of n log n that we have here is actually the best possible worst case and average case time complexity you can have for a sorting algorithm that compares n comparable objects. So if you're wondering where the benchmark is for like, okay, what's the most efficient sorting algorithms, we're right at that cusp. Like this is the fastest you're going to be able to accomplish this for n comparable objects. Now, if you specialize the data types, then there's other kinds of sorting algorithms out there. For example, there are non-comparison-based sorting algorithms. So all the algorithms we've talked about up to this point are comparison-based sorting algorithms. So things like insertion sort, bubble sort, selection sort, quick sort, merge sort, these are all comparison-based sorting algorithms because they work on comparable objects. So that's a very broad class of objects you can work with, and it's the broadest way I can define this problem to you. But when you specialize it, you can probably come up with faster algorithms. For example, if you have working only with integers and they're only of a specific size, like you know the number of bits they're going to be used there, and it's something that's not too big, you can actually come up with linear time algorithms in that case, but it suppresses often large constants in practice. So you may have heard of these. Some of them are called like bucket sort. There's another one called radix sort. I'm not going to be covering those here, but another thing I wanted to point out to you, just because it's on the topic of merge sort, there's other sorting algorithms out there as well that are comparison based. Another one, for example, is tim sort. It's one called tim sort. It's actually used for those that are, say, Python enthusiasts. The sorting algorithm that is in the library for Python, so the Python scripting language, or sorry, not scripting, interpretive language, my apologies. Tim sort is used for the sorting function in that case. It's actually built on the back of merge sort. So if you're wondering how tim sort works, I'll give you the basic idea. You start off with the idea of merge sort, because the whole idea here is that we cleave it down. But the thing is, it's rather oblivious to the best case scenario. Don't notice it's still going to be big O of n log n in the best case even. I would like to bring that best case down to linear time, just like other algorithms like insertion sort and so on. Like in the best case, they could just simply sweep through and if it's sorted, right? Well, I would like that to happen with something like merge sort. And what tim sort does is it actually resolves this. So it could actually have the same time complexity in the worst case, but in the best case, it brings it down to big O of n. But I'm not going to focus on this. I'm just bringing this up as a remark. I won't test you on tim sort or anything like that. Just be very clear. I just feel like I wanted to mention it to you. So what tim sort does is it actually combines two ideas. You know what insertion sort is, right? What it does is it combines it with merge sort. So the whole idea is that because remember, we're being rather oblivious how we cut these things up. What if we knew more information about what's going on inside of these partially sized arrays? And that's what tim sort attempts to do. Just as a fun example, another sorting algorithm, this is one I most certainly talk about in CS340. Another algorithm that can meet this big O of n log n is called heap sort. So this actually runs also in worst case and average case and so on in big O of n log n. This algorithm actually uses a data structure called a priority queue. So it's a generalization of a queue. I talk more about this guy in CS340. So you see this guy in 340. But the neat thing about heap sort, for example, is it is a true in-place algorithm. So it does not create any other data structures. It is just the array itself, and it uses this idea called a heap, hence its name, to actually build a specialized structure that allows it to perform the sorting all in place in the array. So there's none of this cleaving business or anything like that. It's something you could purely implement iteratively. It's really slick algorithm. So if you're looking at like the best candidates for when it comes to the things that we've seen so far, there's quicksort, very simple to implement. In practice, works quite well. But keep in mind, you have to think about the data you currently have. Merge sort has the best known worst case running time. It is optimal in that sense. There's other algorithms out there like heap sort, for example, that are able to achieve that same result. So that's everything I have to say about sorting. Are there any questions? But the big things I want you to focus on when you're thinking about this course, quicksort, merge sort. Those are the two I'm going to test you on. Excellent. Are there any questions? Are we excited for our next topic? Give me 2 thumbs up if we're good to start talking about our new topic. Okay, so we're going to be moving on to talking about an important data structure, well, in particular an abstract data type that we're going to be studying a lot in this class. So if you're wondering what the remainder of this course is going to look like, is we're going to focus on a different abstract data type that it appears in many, many applications. Everything from POS systems to accounting systems to general query-based systems. Like if it involves queries, usually something like this is a fundamental way of representing that. So we're going to talk about what we call dictionaries. Sometimes they're also called a map. So if you ever heard of the concept of a map before, it's the same thing. So we're going to talk about dictionaries next. And every one of the main problems we're going to focus on are going to be centered around this idea of a dictionary. So this is, by the way, sometimes called a map. Just to be clear, some libraries actually will call it a map. So, anyways, let's talk a little bit about what a dictionary is. So it's going to be a model of a searchable collection of records each a pair. So each one's going to be a pair. We're just going to have a key and a value or data. So sometimes I'll call this a data, sometimes I'll call this the value. It's going to be a pair like this. So all of the elements that are going to be going into this dictionary are going to have two components to them, a key and a value. So usually in the case of a dictionary, it's usually presumed that this is going to be dynamic in the sense that records are going to be added and removed or potentially updated. But I'll focus primarily on adding and removing. They can be added or removed. And the biggest catch with this is that these keys have to be unique among all the records. So just to give you an example of what would be like kind of candidate examples of a dictionary. Well, hence the name. A dictionary is just, it's pretty darn clear what it might mean. But say, for example, consider the idea of a student database. So everyone in this area that we're in has a student number, right? All of those are unique to you, right? So what these serve is as actually keys. So say, for example, I want to access student records. I have a unique student number I can use to find that information. So for those that are interested, say, for example, in data, what does this sound kind of like? Does anybody have any ideas of what that might sound like if you have a fascination with things like data? So what does this dictionary thing sound kind of like? I'll tell you, it's something really, for people that are really interested in maintaining data, there's this thing out there, starts with a D, and very often if you want to update records in it, remove records, a database. So it's a very natural way of me to abstract away the idea of a database. So that's one of the killer applications of the dictionary, is that you can view it like a database. So obviously here we're not going to be, this isn't a database course, but the point is that you're going to see a lot of basic ideas that build up to what would be considered a database. Excellent. So in the context of a database, you would call these keys the primary keys. But this isn't a database course here. I just wanted to get you excited, because what we're going to see in this course, because now we're kind of at the second half of the course, You're going to see me start off with some of the most simplest ways to implement a dictionary. And I'll show you some ways to speed up those things. Then I'll start showing you some more ways to represent the data beyond things like linked lists. And I'm going to eventually our goal by the end of this course is I'm going to show you the data structure that serves as the backbone for many ways of setting up database management systems and some other even things like file system trees. So we'll be working our way up to that, and that'll be where we're going to end this course. Hopefully that gets you kind of excited. So I know it gets me excited every time I say it. So and all the keys must be unique. Must be unique in the dictionary. So just to be very clear, the values are allowed to be identical among records. It's the keys, these have to be unique. They must not be the same as any other in the dictionary. So these must be unique. The values don't have to be. You can think of the value as an object. You can think of it as just another number. You can think of the keys, for example, as strings or numbers or other things you might even compare. For example, we'll see that there's more specialized ways we can take the dictionary. For example, if we know that, for example, the keys are comparable in the way we've talked about with sorting, you can actually come up with some more efficient ways of doing certain things. So just keep in mind, keys have to be unique. So the convention I'm going to be picking up in this course is that if somebody attempts to put a record in that already exists with that same key, it just throws an error. So that's going to be the convention I'm going to pick in this course. In some other contexts, people will have it where it actually updates the record. So in this context, we're just going to presume that some error gets thrown, but you can easily adjust the idea so that it updates the actual record. Say if you were trying to insert a record with the same key, it might be just presumed to update it. So just keep this in mind. So just to recap what I said, here's some examples. So for example, if you want to make a database, you think of it as a database with student records, for example. Another one, of course, is an address book. Address book, so you have like names attached to addresses. Hence the name dictionary, is that you could also think of it literally as a collection of words, each with their own definition. Or each one of these actually has a collection of definitions associated with each word. In fact, in some applications, the idea of a dictionary is quite literal. For example, on the final assignment in this course, I will give you a large list of English words that you'll get to use to do something fun. And I mean large. It'll be probably much bigger than most things you played around with up to this point. I'm not quite sure about 115, but I'll tell you that the data set's something like, I think it's at least 10,000 or something like that. It's something a little bit bigger, so you get to get your hands a little dirty with this. So, anyways. Oh yeah. I assure you, the key thing is understanding the ideas. If you can understand the ideas, it doesn't matter how big the data set is. That's the thing. So, anyways, I'm going to define the dictionary as ADT. So I'm going to lay out all of its operations, and when we study the dictionary, we're going to only talk about these operations, okay? So there's some of them that I will also include in here that we're not going to focus on because you'll spend a little bit more time talking about them during the lab as opposed to here. And I won't focus so much about them here because they're not really relevant to what we're talking about. So I'm going to start defining the dictionary ADT, and then we'll quickly talk about a couple of ways we could represent them. So the dictionary's ADT is a dictionary. A dictionary D is a set of records or items each with a key, and value or data. And it has the following operations. So I'll say it supports the following operations. So I'm going to list them over here. So I'll focus on the key ones. I had to do it. I'll focus on the key ones here. There's a few others that I'm not going to talk about so much here, but I'll include them in the notes just for the sake of completeness. All these other ones involve the concept of an iterator, which you may see in the labs at some point. But I will not focus so much on that here. So let's list out some operations here. So the first operation is get. You could think of this as a search or find function. So we have get. So if D has a record with key K, return its associated value. Its associated value. Otherwise, return null. So it's just a search function. That's all it is. So I give you a key that I want to find. If it's successful, it will return the value or data. And in fact, very often in practice, if say the records are an actual object, like a pointer to some object, you just return the entire object. Or the pointer, whatever pointer it is to get me to that object, which usually it's the latter. But for example, on the last assignment, you'll see that this will be the case. But for those that are purists, it will just return just the value of the pair. So you look up for the key, you find that key. So for example, if we're thinking of like a student database, if I wanted to find out your transcript or some information like that, I would search using your student number, and I can retrieve the student information from you. So the idea is I get the student information, not necessarily the student number, because I don't need that. I used it to get to you. but like I said, it's just a search function. Next we have put. You can think of this as an insert function. So it just inserts record. So it inserts a record. KV into D. And this is the important part. If no record with key K exists. So remember, you're only supposed to insert it if there's no duplicate key, right? If K is already a key in D, return an error. Now you might ask, Dan, what does that even mean? I'll use the phrase report as opposed to return sometimes, but the ideas should be quite clear. So I do not want to have it try to put a duplicate key into my dictionary. I would like to have some mechanism that tells me that this happened. So one standard way to make it report an error is using something called an exception. You'll talk more about these in the lab. So on the last assignment, you also get to play around with these a little bit. But I have also included some additional resources if you're curious about how you would do this with exceptions. So you would throw an exception here if you're thinking about this in terms of programming. So you'll see more about this, especially on the lab. So you have this insert kind of function, then we have a remove function. So I give you a key. If D has a record, if D has a record O with key K, remove O from D, O from D, and possibly, but I'll just write it certainly, and return the value of O. Again, the same discussion I had about, for example, getting or using the put, is that sometimes we would like to just have the entire object. So just be aware of that. Sometimes there's a little bit of pliability with this definition. Like I said, it's very general and it appears a lot of different places. Otherwise, return the value of O. But if I do not find the record, I would like to make sure it tells me that. Otherwise, a return or report an error. Same idea as I just mentioned a moment ago. So these are your three main functions we're going to focus on. So if we're talking about a dictionary, these will be the three main ones that we'll be studying. But there's also a couple others as well that you might be familiar with. So others include is empty. So you have is empty. You know what? Can somebody tell me what is empty is going to do? Can somebody just tell me? Do I need to write anything down for is empty? You can just see right from this because we've talked about this function before. What does it do? At least what should it do? What should is empty do? Somebody don't be shy, tell me. Tell me. Yeah, returns, yeah, it tells us if the dictionary is empty or not, right? That's all it does. It returns true if there's no records. Returns false if there exists at least one record. And that's it. There's another one, size. Again, it's just the number of records. So this is going to return you the number of records. So it just returns the number of records. Yes, exactly. Very good. So, like I said, there's some optional operations that involve iterators. If you're curious more about iterators, I have some discussion about this in the notes, but I will not assess you on it. It'll give you a good place to start when you're thinking about iterators. C++ does a little bit, what I would argue, a little bit more complex stuff with iterators than I would personally like. Some other programming languages support the idea of an iterator in a way that's a little bit simpler. But most certainly, if you're curious about it, I know you'll see it in the lab. So I know you will see this at some point. But if you find yourself curious about it, this is just an aside I'm going to mention here. The three optional functions that you'll find that maps and dictionaries typically have will involve iterators. The idea, as its name suggests, is it will iterate through the collection. So depending on what the underlying data structure that's being used to implement the dictionary, it gives you a way to go through each one of the records in that dictionary one by one, akin to something like if I had my jacket, like a jacket with a zipper on it, it would give me each successive object every time I ask for the next one. So this is very natural if you wanted to, for example, use a while loop or a for loop. It'll often give you like the start and end of the iterator, and it'll allow you to just simply go through each one. Different languages support the iterator in a bit more specific ways. C++ is very malleable with the way you can use them. But I will not focus so much on them here, but the three optional ones involve going through all of the keys, going through all of the values, and going through all of the records. So for example, if you had like a linked list, this iterator would just every single time you ask it for another element, or you can figure out what the start and end is, each time you request another element, it'll give you the next one. Normally this is managed in C++ as a pointer. That every time you ask for the next thing, it just adjusts where the next pointer, like where the next object will be in the underlying data structure. It's an interesting idea. Most certainly it's like object-oriented stuff up the yazoo. It's good stuff. So are there any questions about these functions specifically? Because these are the ones we'll focus in on. Okay. Because remember, we're going to be seeing a lot about dictionaries for the remainder of this course. So we're going to focus a lot on ways we can implement these dictionaries, and we're going to learn a lot about data structures in this process. So you're going to find that the remainder of this course is going to be very heavily leaning towards data structures. So anyways, if we're okay with that, I want to talk a bit about how we can implement a dictionary. Now, for those that really just aren't really quite getting all of these operations, I've included in the notes a table walking you through each operation. So for example, if I do like a put operation, what happens to the dictionary and so on. Just for the sake of, if you find yourself just needing a little bit more when it comes to that. But what we're going to do is I'm going to spend the remainder of this lecture, just based on the time we got, I'm going to talk about some simple implementations of a dictionary. So I'm going to keep it rather straightforward for us here, and I'll leave more of the details in the notes, because I think that at this stage in the course, we've talked a lot about arrays, we talked about the idea of linked lists before. I don't by any means need to go into a lot of detail about both of these things. But if you want those details, I'll include them in the notes. So I'm going to talk about some simple ways to implement a dictionary, and this will transition nicely into our next main topic. So let's talk about some simple ways to implement a dictionary. So the first one I'll start off with is a linked list. So keep in mind that I'm going to imagine my dictionary like an unsorted list, where the underlying data structure that's being used to maintain an unsorted collection of elements is going to be a linked list. So the first one I'll talk about here is, so a dictionary can be implemented as an unsorted list That S is looking very sad. It looks sort of like it's morphing into a 5. There's some sort of anamorphs thing going on here. Using a linked list. So all we have to do is really just adapt things we know about linked lists for the get, put, and remove. So I'm just going to draw us a fun picture to make this a little easier for us to visualize. Imagine I have a singly linked list. Because remember, I'm just going to be maintaining an unordered collection of elements. What I'm going to do is I'm going to imagine that I have my collection of records that are all going to be objects. So suppose I have some records. Say if I have 7 as the key and D as the value. So suppose that 7 is a key, D is the value. And suppose that I have a whole bunch of these records. So I have 3C, 9B, and I have 5 and A. So I'm going to imagine each one of the data attributes of the nodes in my linked list are going to point at a record object. So an object that is going to be containing the record. So these are going to be my records right here. And now the unsorted linked list is just going to keep track of all of these records as the data attributes in each one of the nodes. So rather than writing anything down too delicately here, actually, let me write something, at least something. So let's think about get first. Can somebody tell me what can you do to, say if I give you a key, and I want to find if that record exists in the dictionary. What can I do? Just keep it very short. So what can I do with this linked list if I want to find that? You just search through it, right? You just traverse the linked list. Perfect, everybody, perfect. So you just traverse through the linked list, right? And if you find it, you just return its value, right? So that's pretty easy peasy stuff. You know how to, so you just traverse the linked list. If a node contains a record with key K, return its value, right? How do I know that it doesn't exist? How do I know? How do I know that this idea works? You reached the end of the list and you didn't find it. That means you had to have visited every single node in the linked list. Exactly. So you guys are pros at this. I don't have to even be here. I'm just joking. I'm just joking. If the entire list is traversed, return null, right? That seems pretty straightforward. For those that are playing around with these linked lists, this should look pretty easy to do. Now, for put, so I'm not going to go so much just because we have only a little bit of time here left. So this is what you would do with get. Put and remove, you can imagine put being just simply an insertion into this linked list. But there's a big caveat with it's a big but. Right? Massive, massive. Okay. Can I just insert at the front of the head of the linked list for the put operation? Can I do that? So I'm just going to mention while you're thinking about that, I'm just going to say that there's more details in the notes for these two. Just see the notes. No, we can't just simply just do an insertion at the front of this head of the linked list, right? Because what if it has the same key as another record in the linked list? So that means I would have to traverse through the whole linked list and find out if it exists in there first. So you're going to find that that's one thing that's going to make this dictionary a little different than a lot of the containers and collections we've seen up to this point, is that we need to guarantee that the keys are unique. If I encounter a duplicate, that's when I throw the error or report an error. And in removals, all you have to do is just find it, right? You just find it in the linked list, you perform a deletion, whether it be at the head of the linked list, tail of the linked list, or somewhere in the middle. Right? Those all seem pretty reasonable. So if we think about put, the thing we have to worry about with put is that we have to traverse through the entire linked list, right? So that means that in the worst case, put's going to take big O of n time. Regardless, you still have to take linear time because you have to examine the entire linked list to do the put operation. Again, if you think about get and remove, the main reason why we have to be careful here is because get and remove may actually not find the actual record in it. That means it has to traverse through the entire linked list again. So both get and remove also take big O of n. So I'm going to leave you with one last thing before we go, is let's think about what would happen if I sorted. Say if instead of imagining this as just an unsorted linked list, imagine if I made it sorted. Say if it's a sorted array. Actually, let's make it a sorted array even. We'll go even further than that. Can we improve any of these operations? So when we come back next time, I'll talk a bit more about that. And then we'll start talking about our new topic, which will be hashing. So say thank you very much and have yourself a beautiful day. I'll see you later.